the recorder's on and it's 9 o'clock. I'm going to get started with the lecture. I got some feedback yesterday from another class, from cisp310. Apparently, passing the roll sheet around in the middle of the class or close to the end of the class is distracting, and people don't like that. So what I'll do is I'm going to pass the roll sheet at the beginning of the class. All right. Okay, so what we'll do today is I will talk about the new homework assignment first. You can see that here already. Some of you probably guessed that that would be the next homework assignment. Yes. It's a hardware divider, okay? And it's, well, in some way it is structured like a multiplier, but it's slightly more complex. So let me just click on that one, and you can see what kind of components you can use and what is the size of the problem. Okay, so this is the counterpart to the hardware multiplier, except that this time we are dividing unsigned numbers instead of multiplying unsigned numbers. Make a divider that has input pins for a 4-bit dividend, a 4-bit divisor, and output pins for a 4-bit quotient and a 4-bit remainder. Okay, so it's not going to be, in terms of the width of the operands, it's not going to be any worse than the one before, than the multiplier. But a divider is harder to implement, so there will be more components. You can utilize the following components, and you can see none of these components is the actual divider that you can use in logic sieve. Okay, that would make sense, right? So you can use any number of wires and splitters. Okay, splitters in particular can be very helpful, can be useful in this case. Any number of subtractors. Okay, so you can use subtractors, but not comparators. Okay, there's only one minor difference between the subtractor and the comparator. Okay, if you pull those components or look at the documentation of those two, you will see that they're pretty much the same thing. We'll just kind of use a subtractor in place of a comparator. There's some of the outputs you do not need to use in that case, but only one output becomes relevant when you use a subtractor as a comparator. You still have to use AND 2 gates, okay? Because AND is basically how we do multiplication in binary. You have to use negation gates, okay? There's one particular need for a negation gate, but you can use any number of those if you want to. Any number of constants, okay? Any with any type of constants. There are ways to use only just one single constant in the entire program, because you can use negations and you can also use splitters and mergers, okay? Because those things can basically give you any number of constants of any width of any value. But for convenience, it is nice to have, okay, I'll just let you guys use any number of constants, okay? So that's just for convenience purposes. We will go over this the concept in today's class, okay? But I'll do so using the whiteboard, so you might want to write some notes, okay? The design will be slightly more complex than that of the multiplier. The use of subcomponent or subcircuit is encouraged, okay? You can actually use a subcomponent or a subcircuit in the multiplier, but because the design is not that complicated, you can just put everything into one sheet and it will still be okay. Okay? If we have enough time today during the lecture, I will give you the solution to the multiplier just the way I do it. Okay? There are many ways to do it. Okay? There are many ways to do it. You can use like 3 8-bit adders. Okay? Then you don't have to deal with the carry and stuff like that. You just have to shift stuff around a little bit. But if you do that at Intel, you'll get fired, because if you use unnecessarily just the widest width of adder when you don't need to use that, your employer or whoever is making the chip is going to say, hey, you're wasting die space, you're wasting silicon, and that's expensive. Okay, so you don't want to do that unless you have to. Okay, so we'll talk about the design if we have time at the end of the class, but right now we're going to focus on division. Okay, so when we do division, I want to do division with base 10 number first. Okay, because we already know base 10 numbers, so it's nothing new. Do you guys want to turn on all the lights, or is this still okay? It's fine. Okay, so we'll do a base 10 division. I'm just going to randomly pick a number, 6,281, and let's divide it by 37. Okay. So this is completely just random. Okay. Now using heuristics, we already know that there's nothing here, okay? Because we can see that 37 is a 2-digit base 10 number. 6 is a single-digit base 10 number. There's no need to consider it, right? But if you want the procedure or the steps to be transferable to silicon in base 2, we're going to do it anyway, okay? So you look at 6 all by itself, okay? And then you ask, well, is there a 37 in 6? The answer is no. So what do? You put a 0 here. And most people do not write down leading zeros, right? But I'm going to write it down anyway. And with a leading 0 of here, basically saying there are no 37s in 6, I'm still going to end up with a 0 here. That's what I'm going to do. Because I want this process to be transferable to be implemented in silicon in base 2. This is all in base 10 right now, okay? So, come on, Pac, we don't need to do this, right? 6 minus a 0 is 6. Then what do? Well, you pull the next digit in, so now it becomes 62. And then you say, how many 37s do we have in 62? The answer is, well, there's 1, okay? Now, this part is actually difficult in base 10, because if you look at a particular number like 62, and you ask yourself how many 37s are in 62, you are actually going through multiplication in your mind really quickly and just go figure out, oh, okay, I think there's only 1, okay? We can do this because we have had years of training in multiplication in our mind. In other words, we are doing a very short division in order to figure out there's 137 in 62. Okay, here we go. You do the subtraction here. So here's a 5, and it's a borrow, so 25 is the remaining portion. And also, at this point, we have to take the 8 down here, right? So now we have to do a mental division of 258 divided by 37, okay, which is about 6-ish, okay? So I don't quite know whether it's 6 or 7. No, 7. Oh, it's just 1 short of 7. Okay, it's just 1 short of 7. If it's 7, this would be 259. Okay, so it is actually just 6. But see how difficult it is to deal with base 10? Because you actually have to do the division in your mind, and sometimes it's not that obvious. Like this one, it's not really that obvious, okay? So this one only has 6, so we have a 2, this is 42, and 6 times 3 is 18 plus 4 is 22, so we have 2, 2, 2. And then you do the subtraction. I'll carry out the rest of the number up here. 8 minus 8 minus 2 has a 6. 5 minus 2 has a 3. 36, okay? So 3, 6, and then we pull the 1 down from the least significant digit, okay? So we have 361 divided by 37. And this one is kind of more obvious. I think we have 9 of those. Okay, so we have 9 of those. 9 times 7 is 63, and 9 times 3 is 27. 27 plus 6 is 33, I think. So now we have 8, 28. So we have a remainder of 28. Okay. So is that okay so far? Okay. Does everybody did this help remind everybody how to do division in base 10?
Yes.
Because I know most of you have been using your calculators for the past, 10 years or so. So you may not remember exactly how to do division, okay? All right, so this is how we do division in base 10. And can anyone imagine how we are going to do division in base 2? Same way, except easier, right? Okay, so let's try out, a division in base 2 and see how much easier it really is when you do it in base 2. Can I erase this?
Yes.
Okay. All right, so let's go ahead and do this again, but this time in base 2. Okay. And I'm going to turn on the lights just so that we can see better. Sorry, I got it right away. Actually, that's the back that I like. There we go.
That's good.
All right. I already asked the dean to buy me one of those overhead thing. You know, it's an electronic device. It looks down. It's a camera. You know, you can look at a piece of paper, and then I can project it onto the projector and also have it recorded as well. I bought one myself. It's a not so expensive model, and it doesn't work out the way because it's the way I want it, because it's really slow. So when I try to draw something, you know, all I can see is a blur, okay, and then half a second later you can actually see what I'm drawing. The really expensive ones, you know, can do it in real time, so you can actually see what I'm drawing, you know, on a piece of paper in real time. So I'm gonna wait a little bit until the department has money to buy something like that. It's not really too expensive to the department, but I don't want to buy it myself because it's one, it's, you know, it's kind of big. I don't want to have to haul that thing around all the time. All right, base 2 division. So this time I make it a little bit smaller, okay, so I don't have to wrap around like that like the other time. So I'm gonna try, you know, 0, 1, 1, 0, and let's make this a longer division, okay? So I'm gonna make this a 8-digit. So this is actually more complicated than what you would have to deal with, because you only have to deal with a 4-bit dividend. So 0, 1, 1, and let's divide it by 1, 1, 0, 0. Okay. So this is the division I want to do. Everything is in base 2, okay? It's the same way, okay? So the first thing you do is you look at the most significant digit of the dividend, this particular 0 here, and you say, how many 1, 1, 0 zeros do we have in just 0? The answer is pretty easy, okay? We got 0 of those. Okay, fine. But you still go through the entire motion, okay? Because you want to say, oh, 0, 1, 1, 0, 0 will give us a 0. And 0 minus 0 is a 0. And then we have 0, 1, right? Because you take this 1 from dividend. 0, 1, how many 1, 1, 0 zeros do we have in 0, 1? Once again, the answer is pretty easy. There are zeros of those, so 0 times whatever is just 0, 0. And then you take this, do the subtraction. So now we have 0, 1 over here. And then the next one is to take this one down, okay, from the dividend itself. So we are looking at the 3rd digit from the left. And how many 1, 1, 0 zeros do we have in 0, 1, 1? Once again, the answer is 0. Okay? 0 times whatever is always 0. So the subtraction, after the subtraction, we have 0, 1, 1 left. And now we take the next one down, so we now have 0, 1, 1, 0. How many 1, 1, 0 zeros do we have in 0, 1, 1, 0?
0.
0. Fine. Now this is not being stupid, because this is what your actual hardware has to do. Because your hardware cannot look ahead like you cannot use heuristics or rules of thumb like you can. So you have to kind of carry out the entire long division, preparing for the case when the divisor is just 1. Because it is possible, right? I can give you a divisor of 0, 0, 0, 1. In which case, you really have to, this one can be whatever the most significant bit of the dividend is, will become the most significant bit of the quotient. Does that make any sense?
Can you say that again?
Okay. If I give you a divisor of 1, okay, then the most significant digit of the dividend becomes the most significant digit of the quotient. Because if you divide x by 1, you get x back, right?
Yeah.
And that's why we have to do this part here, because it looks silly when we have a number like this, but it's not silly at all, because your divider has to be able to deal with dividing by 1. Does that make any sense? Sort of? Okay. All right. So let's go ahead and finish this one here. 0, 1, 1, 0 minus 0, 0, 0, 0 will give us 0, 1, 1, 0. And then we take the next digit down, which is a 0 here. So this time, finally, we look at 1, 1, 0, 0, and we have 1, 1, 1, 0 in it. Okay, so we have 1 here, and you do the subtraction, you get all zeros. Okay, and at this point, most of us, okay, looking at this, can just say, oh, we'll pad all of these things with zeros and with a remainder of 1, 1, 1 in base 2. Because we know how to deal with this. This is the application of a heuristic or a rule of thumb. But your subtractor is not only going to deal with this particular dividend and with this particular divisor, it has to be general purpose. So it cannot stop right now. You have to kind of carry out the entire thing so that you can understand the mechanism of doing it. Okay? So with all of these being zeros, we'll pull this one, which is the third one from the right-hand side. We'll pull this one down, okay? And then we look at the 0, 0, 0, 1. Okay, this 0, yeah, this 0 is still important. So we look at 0, 0, 0, 0, 1, okay? And we ask how many 1, 1, 0 zeros do we have? The answer is quite easy. Okay, there are zeros of those things. So we put all zeros down here, do the subtraction, then we have 1, and then we pull the second one from the right-hand side over here and pad the rest with all zeros. You only have to maintain 5 digits, by the way. Okay? Because if it requires 6 digits, that means something has went wrong already earlier. Okay? Okay, so we have 1, 1 here, and then we ask how many 1, 1, 0 zeros do we have in just 1, 1 in base 2? The answer is 0. So you do the multiplication. We have all zeros here. Okay, I lied. I didn't have to wrap around. Okay, so now we have 1, 1 left. Okay, and then we take the least significant one down from the dividend, and then we ask the question: how many 1, 1, 0 zeros do we have in 1, 1, 1? The answer is we got 0 of those, right? So we subtract 1, 1, 1. We subtract 0 from 1, 1, 1. We get 1, 1, 1 left. So the remainder is 0, 1, 1, 1 with a quotient of 0, 0, 0, 0, 1, 0, 0, 0. Is that making any sense?
No.
No.
I have a couple questions already.
Okay, go ahead.
The first one is, why are we only having 5 zeros
5
when we're
digits.
bringing everything down?
Okay, think about in base 10 division, okay? So if you have a 3-digit divisor and you're doing the all of these operations here, at any particular time, you will never need more than 4 digits when your divisor only has 3.
Okay.
So it's the same way in base 2.
Okay.
So all of these partial differences only need 5 digits.
Okay.
Up to 5, because the earlier ones don't even have 5, but you still have to maintain those.
All right. So looking at this in reverse, 1100 times 0000100 is going to give us 011001111. Is that correct?
Correct.
The remainder.
With the I mean,
You're shifting by 3 bits, right?
are we?
Shifting by 3.
Well, let's see if this makes sense. Okay, let's see if this if the calculation is working out or not. Okay, so the first thing we'll do to check this out is to multiply 1100 to 1000 and then add 111 to it and see whether we end up with the same number as the dividend. So let's go ahead and do this. Okay, so we'll have 1100 times 1000 in base 2, and that turns out to be a pretty easy calculation because because the second number is 1000. So all we have to do is to shift to the left-hand side by 3 bits. That's all we need to do. So in this case, we just have 0, 0, 1, 1, and pad 3 zeros to the right-hand side. Okay, and then we want to add the remainder to the product of the divisor and the quotient. So we add 111 to it. So now we end up with 11000111, which is exactly the number that we started off with. So the first checksum worked out okay. Okay, so let's do another checksum by converting all of these numbers into base 10 first, and then do the calculation in base 10 to see if it makes sense. Okay, so we have this number here. This is 7. 7 plus no 8, no 16, 32, 64. So we have 96 plus 7, which gives us a 103. Okay, the divisor is 12. So we're trying to divide it by 12. This is the real shorthand of doing division. So we have 9, 12, which gives us a product of 96, right?
106.
Nope. No,
108.
I got it. It should be 8 of them. Okay, so 8 times 12 is 96, and there should be a remainder of,
7.
it should be 7. I just want to make sure. Yep, it is 7. Because 103 minus 96 is 7. So it does work out, okay? 8 is 1000, which is the same quotient that we got in binary, and 7 is 111, which is also the same as the remainder that we got. So everything did work out, okay? So I did not make an arithmetic error here. Okay, so the next question is, how do we do this? If I focus on one particular bit, okay, how can I make that happen? If I look at one bit here, okay, let's just look at this one here, this guy, okay? How do I make this happen? Okay, but I have to remember, whatever gate logic I use, it has to work for all divisions, okay? All 4-bit by 4-bit division, the gate logic that you derive, it has to work for all of those cases, except for division by 0, obviously. Division by 0 is something you do not have to prepare for, okay? Okay, so how do we get this bit here? Well, first of all, it's based on the result of a comparison, right? Because we have to compare this one single digit of the dividend to the entire divisor. Now, I know you're dealing with 1 bit here, there are 4 bits over here. But what if these 4 bits is 0, 0, 0, 1, and this is also a 1? There's 1, 1 in 1, right? So that means just this one single bit here involves the following operations. It involves a comparison, right? What is it comparing? It's comparing the most significant bit of the dividend with the entire divisor. Is that okay? But how do I do this? How do I compare 1 bit with 4 bits? Pad the rest of that number with zeros. Then you compare. Is that okay? After the comparison gives us an idea of, do we have 1 of these or 0 of those? Now that's the beauty of binary numbers, because you can either have 1 or 0 of the divisor. Okay? How do you multiply a 0 or 1 to a number, but only using gates? You already know the answer, okay? The multiplier is already using that logic. Okay, if you look at the list of components that you can use, that's already answering the question. So you will need a comparison. Based on the result of the comparison, you need a multiplication, okay? After you have the multiplication, you have a product. What do you do with the product? Subtraction. So this guy here is the result of a subtraction. This guy over here being together now with the result of the subtraction, that's just a merger or a splitter, right? Because you are merging this number or this digit, this bit, onto the result of the first subtraction using a splitter. Because a splitter is also a merger. It can also merge 2 bits into one 2-bit thing. And then what do you do with this?
Add zeros.
You pad 2 zeros to the left-hand side. You compare to the divisor. Based on the result of the comparison, you can decide whether I want to have 1 or 0 of those. Put the result of the comparison here, but also use the result of the comparison to determine, do I want to multiply this by 1 or 0, and then put it over here. And then you keep going, just keep going like that. your homework assignment is a 4-bit dividing by another 4-bit number. So it's going to be considerably less complicated than what you're seeing on the whiteboard here. But I want to use a longer division so I can show you all the cases. All right? All right, so keeping your eyes on the whiteboard, I'm just going to display the homework assignment again. So I think at this point, you guys have a pretty good idea why we need a whole bunch of splitters, because every single time you have a division, the difference need to be merged with another digit of the dividend to form a new number, and then you can use that number for comparison, okay? And that's why we have subtractor, because a subtractor can also be used for comparing, okay? I'm not going to explain why we need AND 2 gates, because I mentioned that a little bit earlier. Okay, it maps to one of the things I have already written on the whiteboard. There's also a need to use negation gates. That's because of the result of subtraction or comparison. Okay, you guys will figure it out. Okay, by the time you try out, oh, let me see if I can use a subtractor to find out which number is bigger. One of the output of a subtractor has the wrong polarity as a multiplier. Well, it's a good thing that this is getting recorded, because there's no way I can actually repeat my own sentences. And you can use any number of constants. I don't think you need a lot of constants. Most of the constants are only needed for shifting, in this case. Okay? So for the most part, you don't really need a whole lot of constants. Like, you need constants for the first 3 digits, because you need to shift in additional leading zeros for the comparison to happen. Okay? But for the rest of the number, I really don't think you need a whole lot of constants for shifting. All right? And also in this case, you do not need to use subcomponents or subcircuits, because you can make a subcircuit in Logic Sim, okay, that can make your design look a little bit cleaner. Okay, if there's a certain thing that you have to do over and over again, you might as well make a sub-circuit out of it and simplify the design of your divider. It is not required. It's just that if you don't do that, you might have a really kind of busy page, because there will be a lot of components. There will be more components in a divider than there are in a multiplier. All right. Oh, this is also important. I put this in because I saw a lot of designs up to this point with input pins unspecified. Okay, that's not a good design decision. Okay, so you want to make all the input pins specified. Okay, put a 0 to it, put a 1 to it, but don't leave it hanging and unspecified. Okay, that particularly applies to the carry in or the borrow in of stuff. Okay. Are there any questions about the homework assignment, the divider homework assignment? No questions?
Is it due next week?
Yep, you have 1 week to work on it. And knowing some of you will be done by the end of today's lab. Because I think you guys are already quickly formulating, the circuits in your mind. At least you can draw the connection. Okay, I think this component and that component will be needed for this part of the division. Once you know how to deal with the first few digits, the rest will be pretty easy. Okay, because it really is just shifting things around. But for the most part, it's the same mechanism. Yep.
Multiplexers and demultiplexers are allowed, right?
You don't need multiplexers. Nope. I don't think it will be helpful with multiplexers.
Okay.
Mm-hmm. Yep.
So do we need to state the remainder also? The remainder?
Yes, you will need to have pins for the remainder. Okay, so both your question and your question are answered in the assignment itself, because for your question, the output pins will involve a 4-bit quotient and a 4-bit remainder. So those would be the output out of your circuit. And then to your question, you can utilize the following ingredients, which means the other components cannot be used. Otherwise, I wouldn't specify you can't use the following, right? So the implication is the other components cannot be used. All right. So are there any questions about? Yeah, go ahead.
It's because somehow multiply it by 0. I'll multiply it.
There's no division by 0. You're guaranteed that you're not going to be divided by 0. Okay. Any other questions related to the hardware divider homework assignment? Any questions? So can you guys guess what the next one is going to be? Maybe square root, log.
Yes,
No, this is going to be the last one. Okay, this is the last arithmetic, hardware component that we're going to do. All right, so with this out of the way, I'm going to show you how to do the multiplier. Or do you guys not want to talk about the multiplier?
Talk about it.
Sorry?
Do it.
Do it? Okay, so let's go ahead and do the multiplier. Okay, I know most of you already know how to do it. You have turned it in, and some of you have turned it in for an entire week already. But let's go ahead and just do this. Because I want to show you, how to abstract it, because you can have one subcircuit that is really helpful, okay? The one subcircuit that is going to be really helpful, I'm just going to add it here. I'll call this AND, A-N-D, AND, and this is 4 by 1, okay? It is an AND gate, but it's a 4 by 1 AND gate, okay? This is how it works. We go to the wiring. We pick out an input pin, but I will need 2. So 2 input pins, but the fun part is, well, let's make all of these face south, just so that they look a little nicer. But with one of these, I will increase the number of bits to 4. Okay, so we have 1 4-bit input pin and 1 1-bit input pin. Okay, and hence the name of 4 by 1. Okay, because I am using that one single bit on the right-hand side to end with every single bit on the left-hand side. So this makes the design look a little nicer because everything just kind of looks better this way. It's not necessary, so if you look at your own design and go like, well, I did not use anything like that, that's okay. Okay, this just makes it look nicer. And you might find something like this in the divider homework assignment. You might actually find something that will work, 1 or 2 components that will fit into this category. Okay, so we shrink the number of input pins to 2 and make it face south, okay? And we'll need 4 of these, so we'll duplicate like so. There we go. All right, so with this one, I have to split it into 4, so I need to go get a splitter. So splitter goes here, and I want it to face south. And increase the number of bits to 4, not 5, 4. Give me 4. Fan out is also 4, so 4 individual bits. And we'll stick it here, okay? All right, so now I have the basic design here. This 1 bit goes to every single one. So this is basically kind of like a bus. There we go. All right. So this one goes to every single one of the ends, and these go to every single one, but each individual bit goes to each individual conjunction or AND2 gate. And it just works out pretty well this time. I mean, everything looks kind of semi-symmetric. There we go. So the output out of the AND gates will also be merged into a single 4-bit output pin, okay? Because that makes it easy to deal with. Okay. So we'll have one single output pin, and we'll make it face north. It's going to be 4-bit wide, like so. And we'll also need a splitter. So I'll just take this one, and make a copy of it, and then just reverse the direction. So make this face north. So this way we can merge those 4 into 1. I'm just lining up things to make it look nice. Usually I don't care. that's not what I want. I want to go up one notch first. There we go. All right, and of course, this has to connect to here. And it says error because the input is not specified. So if I put all zeros here, the output is a 0. If I put a 1 here, then the output is the same as the input. Okay? Does everybody see how this may be useful in the multiplier design? Because I'm pretty sure most of you, if you do not use this as a subcircuit, you will have 4 cases of these, right? Because you end up with like 16 AND2 gates. Okay, so this makes it just look nicer, on the in the overall design. It's not required, by the way. Okay, I think I emphasized that already. So we want to edit the appearance of the circuit, and the only thing I want to do is to identify, which one is a 4-bit and which one is a 1-bit. So if we click on this one, click on it. This is the 4-bit. So I'll just kind of document this is the 4-bit, because otherwise it's a little bit harder to see. This is the 1-bit. Okay, so here's the 4, and that's the 1. And this is the output. The output, I think I can just leave it undocumented like that. All right. So now I have a subcomponent. Okay, I have a subcircuit that will kind of make the overall design nicer. Okay. All right. So with this subcircuit, I can probably turn off the whiteboard. Right? So the contrast on the screen is a little bit better. It would be nice if I had a remote control, so I can actually do it from all the way over here. But exercise is never a bad thing. All right, so now we can go back to the main design here. The main design has 2 input pins. Each one is 4-bit wide, right? Okay, and we'll make one like this, and then we'll make the other one face the other way. So we'll make this one face west, okay? There we go. And the other one face east. The first one will just keep the numbers, completely intact, as one single wire coming out of it. The other one will split. We'll go to a splitter and split it into 4. And then now we'll utilize the subcircuit that we have created. Okay, so we'll need 4 of these, right? So here's 1, 2, 3, and 4. Okay. So to each one, what I'll do, so I'll stagger these things so they're just easier to see. Okay. Stagger. Oh, maybe not even stagger. I think this will work out pretty nicely without staggering. I have to plan ahead of time, how much space I will need to do all the wiring. Okay. So I think this will work out really well because I can just take one wire. It's kind of like a bus in a way because it connects to every single one the same way. So this is the one that is going to feed into every single of these 4x1 conjunction or AND gates. And then with the other one, I will take one wire for each one. So we'll take the most significant bit going to the first one, the second most significant bit. Uh-oh, that's not good. I think that's a good one. Into this one. The second least significant bit. Need a better mouse. Do you think the department will get me a gaming mouse if I say, well, I can't really use the cheap HP mouse that comes with the computer?
Yep. Yes.
I need a 8000 DPI dual speed gaming mouse. So when I do precision work, I can have a little clutch and say, okay, we need to go slow with high precision now. It's kind of like, sniping mode, right? All right. So now we have, the most of the numbers already, done. Okay. So it's just a matter of putting in the adders. Okay. Now this is the important part is how do we structure the adder? I'll deal with the least significant portion first, and then we'll work our way up to the more significant portion. Okay. In other words, I'm going to take the output out of this 4x1 AND gate and take the output out of this one, and put a adder to perform the calculation. So the first question is, how wide do I need that adder to be? And remember, I want to save silicon. I don't want this adder to be wider than it needs to be. Okay. If I don't really care about optimization, I can make every single adder 8-bit wide. Then I just need to pad the zeros, and I don't have to worry too much about we need to take that carry and use it in the next one. Okay. But I don't want to do that. I want to save silicon. Remember, I want to save silicon. So how wide of an adder do I need to add the output of the bottom 4x1 AND gate to the second bottom? 5-bit. Okay, 5 is what I need. Okay, very good, because we have to shift this one by 1 bit. Okay, so it's a 5-bit input to begin with. So we will definitely need a 5-bit adder. So then we go to arithmetic, pick out an adder, and change the data bits to 5. Oops. Here. And we'll deal with the carry in a little bit later, because the first thing we have to deal with is the input. Okay. This only has a 4-bit wide output. This one only has a 4-bit wide output, so we need a splitter to merge the two into a 5-bit adder by padding with a 0. One will be padded on the right-hand side, the least significant digit. One will be padded on the left-hand side, which is the most significant digit. So we'll need splitters. We'll need 2 splitters. So we'll go to wiring, and we pick out splitter. And this time we'll need a 5-bit wide splitter. And the way they are splitting will be slightly different, but first of all, we will change the direction just so that they look nicer this way. So the first one, I'm going to keep the bit 0 as the top and everything at the bottom. Like so. And somehow, yep, that's correct. And then with the second one, did I make a mistake? No. The fan out needs to be changed. So I need to change the fan out to 2, which is going to reset all the wires. I have to redo it. Here we go. All right. So this is my first splitter. The first splitter allows me to pad a 0 to the least significant digit. Okay. So which AND gate should I put it next to? This one or this one? Which one needs to have the least significant digit padded? The bottom one or the second bottom one? Second to the bottom.
The second.
Second to the bottom. Very good. Okay, so we'll put this splitter over here, okay, because that's where it belongs. So that makes, so I make a duplicate of this, except this time it will be splitted the other way, 4 to the top and 1 to the bottom. And that one, it belongs to the bottom. Okay, so I take the output out of this 4x1 multiplier. Basically, it's a multiplier because we're multiplying a 4-bit number by a 1-bit number. That's what an AND gate is. Okay, and actually, I better start erasing stuff because I will be doing your homework assignment. Okay, there we go. Now I feel better. By stating, oh, I need to erase this because I'll be doing your homework assignment, I'm actually doing you a favor because I'm indicating which part of the homework assignment I'm talking about. Not only am I giving you the solution, I'm also telling you which part. So, all right. So we'll take the 4-bit output out of this thing, hook it up here. Take the 4-bit thing output out of this, hook it up to here. The rest are all zeros. I'm not too concerned about the zeros. I'll have one single 0 to handle all of this stuff. Okay. So the output out of this is 5-bit wide. We'll put it into the adder. The output out of this is also 5-bit wide, and we'll put it into the adder like so. Okay. So the two numbers are now dealt with. The output out of this is a 5-bit number with a carry that is actually useful. Okay? So it's actually a 6-bit output out of this adder. Is that making any sense? Because if you have 1111 with a 0 padded to the right-hand side plus 01111, then how many bits do you need to represent the end result? You need 6. Okay, so let's try this out. Okay, 0 plus 1 is a 1 with no carry. 1 plus 1 is a 0 with a carry. 1 plus 1 is a 1 for the carry, and then 0 plus 1 is a 1. 1 plus 1 is 0 with a carry. 0 plus 1 is a 1. And then we have 1 plus 0 being a 1. 1 plus 1 being a 0. And we have an extra carry here. Okay, so the output is a 6-bit output, which means this carry, the carry out of the only adder that we have up to this point, is useful. Okay, we need to use the output carry for something. Okay. The rest of this is not going to be very exciting because all we are going to do is to, kind of replicate the design here, except now we're dealing with, 6-bit wide with, let's see, how am I going to do this? Well, I have a few ways to do this. I'm going to do it this way. We have to pad the least significant 2 digits. So we'll split those 2, and then the rest will be the bottom. Okay. There's a particular reason why I want to do it this way. Okay, so you guys will see later on why I'm doing it this way. Kind of keep the same geometry here. And then the last one is going to be about the same, except this time we have 7 bits wide, and we'll split it in fan out would be 4. So we have 0, 1, 2 for the least significant digits, and then everything will be at the bottom. Okay, so like that. Oh, it just made that connection that is not intended. Get rid of that. Okay. All right. The output out of the first adder has to go to the second adder. So we'll leave some space for the second adder. Okay. So we'll take a second adder. This one is a 5-bit adder, so the second adder is going to be a 6-bit Y adder. So we'll take another adder here, turn it into a 6-bit adder. So, all right. So immediately we have a problem because the output out of the first adder, which is the one to the left-hand side, is only 5-bit wide. Okay. But the input to the second adder, which is the one on the right-hand side, is 6-bit wide. Okay? Well, that's okay. We can deal with that because the most significant bit is just the carry out of the first adder. Okay? So, but to do this, we need another splitter to do this. Okay, so we will need I can just replicate this one here. So I'm replicating this adder. We'll turn it into a 6-input splitter. And the most significant bit is the one that has to be on its own. Everything is to the top, like so. And it's going to look a little bit funny because the output is here. So the output, well, let's see. How am I going to do this to make it look nicer? There we go. There we go. Okay. And the output out of this one feeds into the input of the second one. There we go. What about the other input here? Yep. It will just be one of the results of here. And remember, all the zeros, I'll deal with all of those later on. They're not a big issue here. I just have to remember to do it later on. There we go. So now we are done with the second adder. It's time to work on the third adder, but you can probably see the pattern already. Okay, the output out of the second adder will have a merger to merge into the input of the third adder, which is going to be a 7-bit adder. And then the other end or the other input is going to come from the top 4x1 you can call this a 4x1 conjunction gate. You can also call this a 4x1 multiplier. Okay, because that's basically what it does. So now let's put that on. Control-C, Control-D to duplicate, and turn this into a 7-bit adder. We'll use about the same type of geometry here, just so that they look about the same. So we'll need another splitter and stash it about here. Turn this into a 7-bit splitter, and we'll split it so that the first 5 bits will stay together. The most significant bit is coming from the carry out of the second adder, and then the output out of this will feed into one of the inputs of the third adder, which is also the only adder left to do. And then the output out of this is going to go to, this is looking nice, it's looking very symmetric to me. And we'll have this going to here. All right, so we're almost done with only one little thing left to do. The output out of this is going to be go to the output pin, so we'll specify an output pin here, make it face north. We'll need 8 bits here, and we also need a splitter to kind of merge the output of the last adder with the carry out of the last adder. So in this case, we want it to face north, 8-bit wide, and fan out to 8 individual inputs. Nope, 2. 2 is all we need, and we'll have everything to the right except the one carry to the left. There we go. So the carry is going to the most significant bit, which is bit 7. The actual output, which is bit 0 to 6, will go to bit 0 to 6 of the merger. And then the output of the merger will go to the output pin, which is also 8-bit wide. All right, so there's only one thing left to do. What is it? All the zeros, okay? I only need 1 0. So how do we get that 1 0? In fact, there is a way, well, let's see. No, I cannot do this because of all the components that I allow you. Well, there's a way to do this, okay? I can make a 0 without actually a constant of 0. Trick question, how do you do it?
Input pin? Input pin?
Input pin? I can tap any pin here. I can tap any 1-bit pin here and turn it into a 0 because of one of the gates that you are allowed to use. The AND gate. Okay? Okay, I'm going to show you exactly what I mean by that. Okay? So I don't even need a constant of 0. Now don't do this when you work for Intel, okay? Because your boss or your supervisor would just say you're a smart ass, but you're wasting silicon and you will be fired. Because the worst thing you can do at Intel is what? Wasting silicon. Okay? You don't want to waste silicon. All right. So this is how you can do. You can make a 0 out of just a not AND gate. So I will put an AND gate here. This is funny. I cannot stop laughing. Okay. So we'll put an AND gate here. Change the input to 2. I think some of you probably know what I'm planning to do already. Okay. So we'll turn it into an arrow one. And here's the trick. We'll negate one of them. Okay. So we'll attach both of these to the same pin, so the output is guaranteed to be a 0. So here we have a 0 without using a constant of 0. How do I make a 1? Well, you take the output out of this thing here, and then you use another AND gate, except both inputs or just the output being negated. So that one is guaranteed to be a 1. And then by the use of splitters and mergers, you can make up any constants now, because you have a 1, you have a 0, and you have ways of combining zeros and ones. So now you can actually make any constants you want, except it's really kind of like a long and roundabout way to do things, right? But sometimes it's fun just to know that you can do this, okay? As long as you don't do it while employed at Intel, you'll be fine. All right, so now we just attach this 0 to everything that needs to be connected to zeros. So these two, we can merge them first. And these three, same thing, merge these first. I think I did a pretty good job making this design kind of symmetric today. This is my artistic day. And then we also need a bunch of zeros to the carry in. So there we go. 1, 2, 3. Okay, I think I'm done. Let's test it. You guys know me, you know, I can make a mistake somewhere and not realize. Okay, how do we test this? Well, this is already testing it, right? 0 times 0 is a 0. Okay, but that's trivial. So we want something that's a little bit tricky. How about 12 times 12 being 144? So is that 144?
Yes.
It's 128 plus
16.
32.
16.
16? All right, it is 16, sorry. 128 plus 16 is 144. So I'm fairly sure this is working. If you're not sure about this, you can try another number. Let's say 13 times 13, that should be 169. So we have 128 plus 32 plus 6 plus 8, and then plus 1. I think that's 169. All right. So are there any questions about this design? I just think all of you were able to do this homework assignment. It's just a matter of, how do we structure things, and how do you want to arrange it. So you can see in this case, I have not even used a single constant.
Can you go back to your
Assignment?
No, the design of your 4x1.
Oh, sure. The 4x1 is, you can call this a 4x1 AND gate. You can also call this a 4x1 multiplier, because that's basically what it does. The one bit on the right-hand side, the one input bit on the right-hand side, that's multiplied to the 4-bit input pin to the left. Okay, but since it's a binary number, so it's either a 0 or 1, and as a result, you can just use AND gates to do that. So this might be useful in your divider, or one of the components you might find useful in your divider, so you don't have to sprinkle like tons of AND gates everywhere. Okay. Next thing, okay, for your homework assignment, you can go to the library reference, go to arithmetic library, go to Subtractor, and you can say, okay, so out of the subtractor, which one is going to be useful as the result of comparison, okay? So you need to kind of think about this a little bit, okay? Because I'm telling you, between a subtractor and a comparator, they're not really that much different, okay? A comparator is a lot more general than a subtractor, because it can indicate greater than, equal to, or less than. But there are two of these outputs that we don't need, okay? So we can just use a subtractor to do the same trick. The question is, with a subtractor, which output can be used as the result of comparison? Now you also have to keep in mind that we're dealing with unsigned numbers here, not signed numbers. Okay. Are there any questions about the homework assignment or the individual components that you are allowed to use? Questions? All right. So if there are no questions, we're going to go back to the browser and continue our discussion with the flags, because that's where we left off last time. So now we are moving on to the sign flags, the overflow flag, and so on. Okay, so we will look at sign numbers again. But this time we are particularly interested in, okay, so how do we compare numbers? because that's also related to your homework assignment, which is kind of nice because now we can do two things at the same time. All right, flags that are affected by subtractions and comparison, because comparison is just subtraction but without storing the result. Okay, the carry flag is, what do we use the carry flag for in subtraction? It's also known as the borrow flag. So from here on, the carry flag and the borrow flag are basically the same thing. Okay, but under what condition is the borrow flag going to be set? Think about the meaning of borrow. I'll do it using a text edit. Okay, so let's switch to my. I don't have one yet, so I'm gonna make one. Here we go. Okay, so think about subtraction. When is the borrow going to be set? The overall borrow, not the individual ones in between. Okay, the last borrow, the borrow out of the entire subtractor. When is that going to be set?
When the second number is bigger than the first number.
When the second number is bigger than the first number. Okay. Okay, I think that just answered one of the questions related to your divider homework assignment. Okay. Okay, let's go through a few calculations here. So let's try 0, 1, 1, 1 minus 1, 0, 0, 0. Okay. And this is, the subtractor does not really care whether these are signed numbers or unsigned numbers. That's the beauty of 2's complement, okay? Because we don't need the special consideration. We just carry out the same type of subtraction mechanism. So this is the usual way I do it. And we'll just go ahead and do the subtraction, okay? 1 minus 0 is 1 without any borrow. 1 minus 0 is a 1 without any borrow. So this borrow is going to be a 0. And the same thing happens here. Okay? So the first 3 digits are fairly boring. Nothing really happens. The last one is 0 minus 1 being a 1. Oops, 1 with a borrow. 1 minus 0 is a 1. So now we actually have a borrow here. This borrow indicates that the second number is larger than the first number, and that's why we have to borrow from a digit that does not exist. Is that okay? All right. But this result of conclusion, this conclusion that the second number is bigger than the first number, only applies when you interpret the numbers in an unsigned fashion. Okay, you cannot draw that conclusion when you look at 1, 0, 0, 0 as a signed number. Okay, that was a question. Go ahead.
I'm a little just confused. When you were subtracting the third digit, why is that a 1 on the out? So you have the
Oh.
two,
Oh, yeah, that you're correct. Okay. Thank you. All right. Okay, so now you want to look at this, as numbers that are signed and unsigned. What is 0, 1, 1, 1 as a unsigned number? It's 7. What about 1, 0, 0 as an unsigned number?
8.
That's 8. Okay. Go. And 8 is greater than 7. Okay, so the conclusion is right. Okay, the second number is greater than the first number and the borrow flag is set. What about signed interpretation? What is the signed interpretation of 0, 1, 1, 1? It's still 7, right? Because the most significant bit is a 0, which means it is a non-negative number. What about 1, 0, 0, 0, where the most significant bit is a 1? That is representing what value? Negative 8, exactly. So we have negative 8 here, and negative 8 certainly is not greater than 7. So that's why, using the borrow bit to indicate the result of a comparison only works for unsigned interpretation. It does not work for signed numbers or signed values. Are there any questions about that? Okay, no questions? Okay, yep, go ahead.
How do you deal with this sign? with the sign?
That's a good question. That's actually what we're going to do for the next 15 minutes or so. We'll look into, how do we compare signed values, okay? Because unsigned is easy, okay? One flag is going to be able to do it, okay? If you just want to see whether the second number is greater than the first number, that's all we need. But tech, don't we also need some of the other comparisons? Don't we also need to check for equality? Don't we also need to check whether the first number is greater than the second number? No, not really, okay? Think about this. In C and C++, how many comparison operators do we have? Operators that will allow you to compare two numbers, two values. How many do we have? We have less than or equal to, greater than or equal to, and not equal to, right? There are 6 of those, right?
Yes.
What if I tell you only need 1?
Less than?
Less than is all you need. Why?
Because if it's not, then it's
Well, okay, let's answer that question first, because I want to tell you guys, why a single way of knowing the result of comparison is all you need to do the other comparisons. Okay, so let's say, this is the only thing you have, okay? But you also have the other logical operators. In other words, you have conjunction, you have disjunction, you have negation. So you still have those. All right? Okay, so let's see how we can do the rest. Okay, so x is less than y is trivial because it's using the only operator that we have. So, but just for redundancy, we'll say x is less than y is x is less than y. It's only using the operator we are allowed to use. What if you want to check whether x is greater than y? Well, flip the order, right? You check whether y is less than x then. These two are equivalent expressions. Okay, that's easy. What about x is less than or equal to y? Well, then you check for the negation of y is less than x. Let's see, is that right? Yeah. Because x is less than y is really the same thing as saying, is it not the case that y is less than x? Is that making any sense?
But it isn't also the case that if x is less than or equal to y,
If x is less than or equal to y, x is not greater than y. That's basically what it's saying.
you have less than still.
Yeah.
Greater than's the other way.
No, x is less than y
Oh, okay,
is
no,
the
no.
same thing as
Yeah.
x is greater than y. Yeah. Okay, so next thing is x is greater than or equal to y. That's easy. We just flip the order, right? Because if x is greater than or equal to y, that means x is. Oh, it's not the case that y is greater than x.
The less than.
Oh,
Less than.
but I have to change the order. Yep, there you go. Because I want to only use less than, right? Okay, now we move on to the seemingly more tricky ones, which is, what about x equals to y? What do you think?
X is not less than y.
X is not less than y, and it is not the case that y is less than x. Okay, last one, x is different from y. Okay, there are two ways to do this. The really lazy way to do this is this. Which is absolutely unnecessarily, complex, which is not what Intel would want. So if you were Intel, what would be the solution that you want? To use the simplest logic to do this.
X is less than y or y is less than x.
Exactly. There we go. All right, so just knowing whether a number is less than the other number is all we need. But we can't even do that with signed numbers easily. Okay? So what I'll do is I'll give you a few cases, and then you guys can kind of think about this a little bit, and we may or may not be able to talk about the solution in today's class. But we'll go ahead and look at a few, kind of more or less, trivial cases. The first one is 0, 0, 0, 0 minus 0, 0, 0, 1. because we are still looking for the cases where the second number is greater than the first number, okay? And obviously, we all know the answer to this particular question, okay? And I think we have carries all the way through. So the end result is 1, 1, 1, 1. Do we have an extra borrow here? Yep, we do, okay? All right, so this is the first one. The second one is going to be, now remember, this is all signed, okay? So the second one is going to be -8 being less than 1, right? -8 is less than 1. So, but we want to see the end result of this, okay? This one I don't even need to go through the individual calculation. The carry is going to be, or the borrow is going to be a 0, and then we'll have 0, 1, 1, 1 as the actual result. Is that making any sense? Is that okay? All right. All right. So I want another case where the second number is greater than the first number. What about both of these numbers being negative? In other words, we are saying, oh, -2 is less than -1. Right? The first number, 1, 1, 1, 0, is representing -2. The second number, 1, 1, 1, 1, is representing -1. As 4-bit numbers, signed 4-bit numbers. Wait, hold on a second here. I'm not 100% sure about 1, 1, 1, 0 representing -2. How do I know, the absolute value or the magnitude of a negative number? First of all, how do I know 1, 1, 1, 0 is a negative number when the number is only 4-bit wide? The most significant bit is a 1. Okay, that's the sign bit, right? Once you know the number is a negative number, how do you know the magnitude, or how do you know the absolute value of that number? What do you do to flip it back to the positive side? What operation would you do? 2's complement. Okay, so we want to do the 2's complement on 1, 1, 1, 0. Okay, so I'm just doing this on the side here. So the 2's complement of 1, 1, 1, 0 is the 1's complement of 1, 1, 1, 0 plus 1, right? 1's complement is the same thing as a bitwise knot. We're flipping all the 0's to 1's and all the 1's to 0's. So it becomes 0, 0, 0, 0, 0, 0, 1 plus 1, which is 0, 0, 1, 0 in base 2, and that really is just 2. Okay, so that's how we know 1, 1, 1, 0 as a 4-bit number using the sign interpretation is representing the value of -2. Okay, all right, but we'll just go ahead and carry out the calculation here, and I don't think we'll need a whole lot of calculations. So the end result is going to be 1, 1, 1, 1 with a borrow flag set. Okay, and I think there's only one more case we have to consider. So far we have non-negative number minus non-negative number. We have a negative number minus a non-negative number. We have negative number minus a negative number. And I think there's one case left, which is, oh, I remember which one. It's 1, 1, 1, 1, which is representing -1 minus 0, 0, 0, 1, which is also a negative number minus a non-negative number. But this time, the result is a little bit different. Okay, so we'll take a look at the result here. I don't think this one takes long to compute. What is the end result of this? 1, 1, 1, 0. Do we have an extra borrow? Nope. The extra borrow is a 0. And we have 1, 1, 1, 0 here. There we go. So now we have all 4 cases to consider. In all 4 cases, including from the top here, we have the second number being greater than the first number. So now the question is, do we see anything in common between all 4 subtractions and say, hey, that is the flag that we are looking for. This will tell me whether the second number is greater than the first number. Do you guys understand what I'm trying to do? I'm trying to identify one single bit, because I'm lazy, where it can tell me whether the second number is greater than the first number. Yep. Go ahead. Okay, so we'll try the easy ones first. Okay, we'll try the borrow flag. Okay, because it seems like the borrow flag is really useful when it comes to unsigned numbers. Does it work for signed numbers? The answer is no, it does not. Because in this case, the borrow is a 1. In this case, the borrow is a 0. In this case, the borrow is a 1. In this case, the borrow is a 0. So when the second number is greater than the first number using the sign interpretation, the borrow itself can be a 1 or a 0. So that's why we cannot look at just the borrow flag and say, oh, we can conclude the second number is greater than the first number. Is that okay? What about the sign flag? Okay, the sign flag, it refers to the sign flag of the result here. The sign flag is a 1 in this case, the sign flag is a 0 in this case, the sign flag is a 1 here, the sign flag is a 1 here. So it's not conclusive either because the second case is the one that breaks it. Okay? Anything else? As it turns out, there is no single flag that you can see here that can make that conclusion. So we need something else. We need some help. Okay. So the help that we need is what we call the overflow flag. Okay. So the overflow flag, which is usually just an O. Okay. But I'm going to use OV here because just uppercase O looks like a 0. Okay. So I don't want you guys to think this is a 0. It's an overflow flag. The overflow flag is a 1 if and only if the sign of the result makes no sense. Okay. Well, that's an English description. Okay. But exactly what does it mean? Let's look at these 4 cases and see which one applies. Okay. The sign of the result makes no sense. Okay. Let's take a look at the first case here. The first case is a non-negative number minus a non-negative number, ending up with a negative number. Does the sign of the result make any sense? Sure, yeah. I mean, 2 minus 3 is negative 1. Okay, so when you subtract a non-negative value from a non-negative value, the result can be positive or not, or non-negative or negative. So it's okay. This one is fine. Let's look at the second case. The first number is negative. We are subtracting a non-negative number from a negative number. The result is non-negative. Does the sign make any sense? It does not. Okay. Let's look at the third case here. The first number is negative. The second number is negative. If I subtract a negative number from another negative number, the end result being negative, does it still make sense? Yeah, it can still make sense. That's okay. The last one is having a negative number minus a non-negative number, ending up with a negative number. It still makes sense. Okay, so that's what the overflow flag is. Okay, so but in terms of gate logic, how do we define the overflow flag for subtraction? There's one case where it doesn't make sense, but it's not a case where the second number is greater than the first number. So I'll present that one last case first, just so that we know, okay, this also does not make sense. So in this case, we will have a positive number, or non-negative number, minus a negative number, ending up with a negative number. So we'll do this calculation. It becomes with a borrow. There we go. So when you look at this, what are we doing? The first one, which is 0, 1, 1, 1, is 7. It's representing 7. The second one is 1, 1, 1, 1, which is representing negative 1. When you subtract negative 1 from 7, what should you get? Positive 8, right? The end result is 1, 0, 0, 0, but because we're using the sign interpretation, this is no longer 8, this is negative 8. So the sign does not make sense in this case. Okay. All right, so can we come up with some kind of gate logic to indicate when the result does not make any sense. So what we'll do is we'll take a look at the MSB, or the most significant bit of the numbers, and also the most significant bit of the result. Okay, this is one way to do it. So when you look at a number, okay, so let's say the most significant bit of the first number is lowercase a. The rest of the bits I don't even care. Okay, we just use question marks to indicate do not care. B, and the end result is C question mark question mark question mark. Okay. I don't even care about the final borrow bit. Okay, that's not important to me. The overflow flag in this case is going to be basically saying if A is a negative number and B is non-negative. If you subtract a non-negative value from a negative value, but you end up with a non-negative result, then the sign does not make sense. Right? Okay, let me say that again. A is not negated, which means it is a 1. B is negated, which means the second number is non-negative. So you're subtracting a non-negative number from a negative number. The result should be a negative, right? But in this case, C is negated, which means it is a 0, which also means the result is non-negative. So in this case, it does not make sense. And then the other one is just flipping everything the other way. If you have a non-negative number to begin with, you're subtracting a negative number from it, and you somehow end up with a negative number, the sign also does not make sense in that case. Oops. See? So this is how we can actually define the overflow flag using bitwise operations. But these are bitwise operations only looking at the most significant bits of the two numbers that you are dealing with in the subtraction, and also the result of the subtraction or the difference. Is that okay so far? Okay, so one thing you can do, we are running out of time today. One thing you can do is to go through all the cases that I have listed here, and then you just use this formula, okay, apply that, and figure out the overflow flag for each case. And then you look at the overflow flag itself and say, can that by itself indicate the result of comparison for signed numbers? Okay. So that's that's your informal, homework assignment. Okay, you don't have to do it, but if you think about it, it'll be helpful. Alrighty, I'll see you guys at the lab. If not, next Tuesday.